Hello students, welcome back to my channel. So this is the third class of real numbers. As promised in the last class, we had to proceed for exercise 1.2 in the current class, but two important questions, question number 4 and 5 of exercise 1.1 were left. I think these are very important questions to be discussed. So let's proceed with question number 4 and 5. Before that, we just need to understand that what is the fundamentals of Euclid's division lemma. Then only these questions will be very much easier for us. So this will be a very short video, but before that I would like to explain the fundamentals of Euclid's division lemma. So Euclid's division lemma is the bedrock of number theory. So it provides a formal way to express the relationship between any two positive integers, which allows us to prove general properties about the squares and cubes of numbers. For any two positive integers a and b, there exist unique integers q. Here we can see that for any two positive integers a and b, here b is equal to 3. That is, the relation should be a is equal to b into q plus r, where r should be either equal to, where r should be greater than or equal to 0 and should be less than b. So there exist unique integers q and r satisfying this particular equation. So here in the expression, a is the dividend, b is the divisor, q is the quotient, and r is the remainder, which can be 0, 1, 2 or 3 depending upon the situation, but it will vary. The value of r will vary from 0 up to the value of b. If the value of b is 3, the r will be either equal to 0 or greater than 0 but will be less than 3. Here the value of b is taken as 3. So if we divide any number by 3, the remainder can only be 0, 1 or 2. As per the condition, r can be equal to or greater than 0, but the value it has to be less than the value of b. So if we'll take the value of b as 3, so x can be equal to 3q plus 0 where remainder is 0, or 3q plus 1 if remainder is 1, or 3q plus 2 if remainder is 2. And now coming to our question, these were the basic concepts that were required to be explained and understood before moving to our question number 4 and 5. The question says that show that the square of any positive integer, where any positive integer, in the examples we had seen any positive odd integer, but here it's not saying odd or even, it is saying any positive integer is either of the form 3m or 3m plus 1 for some integer m. See, this is the question. So here one of the important hint, let x be any positive integer by the lemma b should be equal to 3. Why 3? Because here it is asking for 3m or 3m plus 1 of the form 3m or 3m plus 1. That means the divisor over here is 3. So let us take the value of b is equal to 3. So we'll proceed stepwise in a manner that it will be easier for you to understand the process of solving such questions. Step 1, the setup. X has to be 3q or 3q plus 1 or 3q plus 2, because it was asking, the question was asking the square of any positive integer is of the form 3m or 3m plus 1. Here b is equal to 3. So we'll see for remainder 0, the value of x will be 3q. For remainder 1, value of x will be 3q plus 1. Or remainder 2, the value of x will be 3q plus 2. Now operation. What is the operation? Squaring both the sides. Suppose x is equal to 3q. We will square like x square is equal to 9q square. Okay. Likewise, we'll proceed. The target. What is our target? This is the operation that will have to square both the sides. And what is the target that we have to prove? It is of the form 3m or 3m plus 1. So proceeding ahead, we'll take two different cases. The case 1 where x is equal to 3q, or case 2 where x is equal to 3q plus 1. Okay. So squaring both the sides, we'll get x square is equal to 9q square. Now we'll separate 3 into 3q square. Why? Because we have to prove that we have to take out 3 and the remaining portion will be 3q square. So this is of the form 3m. This here we'll take 3q square as m. In case 2 where we have to prove 3m plus 1, we'll square both the side. X square is equal to 3q plus 1 the whole square. We'll get 9q square plus 6q plus 1. And here after taking out 3 from 9q square plus 6q, because we'll have to separate 1 will come over here and we'll take out the common 3. The remainder will become 3q square plus 2q. This will be taken as m. This particular value will be m. So hence proved x square is also of the form 3m plus 1 when x is taken as 3q plus 1. Now taking case 3 is a bit tricky because where we'll take x is equal to 3q plus 2. Remember, since we have taken b is equal to 3, so r will be 0, 1 or 2. R can be 0, 1 or 2. So 0 case where x is equal to 3q, where r is 1, x is equal to 3q plus 1. Now where r is equal to 2, here x will become 3q plus 2. So squaring both the sides, we'll see 3q plus 2 the whole square is equal to 9q square plus 2q plus 4. Now here we will separate 4 in 3 plus 1 into two different numbers because we'll have to separate one from the equation. One will carry forward till here. Now we are left with the equation 9q square plus 12q plus 3 and 1 is separated. So taking 3 common from this particular equation, we will get 3 into 3q square plus 4q plus 1, and this will be our m, and here 1 has already been separated earlier. So this particular equation x square again becomes 3m plus 1. Hence proved that the square of any given positive integer is of the form, not any positive integer, but the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. We saw 3 different cases. Okay, let's move to the fifth problem where we have to show the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Remember, in the previous problem, fourth problem, it was the square of any positive integer. Here we have to show that the cube of any positive integer is of the form 9m, 9m plus 1, 9m, 9m plus 1 or 9m plus 8. Here it is a very important tip. Use b is equal to 3 in place of b is equal to 9. Why? Earlier it was the divisor was 3, so we took b is equal to 3, but here divisor is 9. So why we are not taking 9 and we are taking 3 in place of 9? Because if b is equal to 9, we'd have to solve for remainders. R is equal to from 0 to up to 9. That means r is equal to 0, 1, 2, 3 up to 8. Okay, so there will be 9 different cases, and which will be a very difficult task and very big solution. Okay, so we are taking only b is equal to 3. And what is the secret behind taking b is equal to 3? Since the cube of 3 is 27, which is easily divisible by 9, starting with b is equal to 3 gives us the common factor of 9. We need by only solving 3 simple cases. Did you get my point? So we'll again, just like in the previous question, we'll have to take 3 different cases where case 1 says a is equal to 3q where r remainder is equal to 0, case 2 where a is equal to 3q plus 1 where remainder r is equal to 1, and the third case will be a is equal to 3q plus 2 where remainder r is equal to 2. Now coming to case 1, moving ahead, we know the formula for a plus b the whole cube is equal to a cube plus b cube plus 3a square b plus 3ab square. Coming back to the case 1 where a is equal to 3 cubes, cubing both the sides, we will get a cube is equal to 27 cube. Extracting the 9, we will get 9 into 3 cube, which is of the form 9m. So simple. So moving ahead to case 2 where a is equal to 3q plus 1, cubing both the sides, a cube is equal to 3q plus 1, 3q plus 1 the whole cube, which comes to 27 cube, q cube plus 27 q square plus 9q plus 1. We'll take 1 out and extract 9 from the remaining equation. So 9 extracted from 27 remains 3q cube plus again 9 extracted from 27q square gives 3q square plus 9 is extracted from 9q, it gives q. This becomes our m, this is 1, hence the cube of any positive integer when remainder r is equal to 1 is of the form 9m plus 1. Now coming to the third case, which is a bit tricky case where remainder is r is equal to 2, so a is equal to 3q plus 2. Cubing both the sides, again a cube is equal to 3q plus 2 the whole cube. We'll expand the expression 3q the whole cube plus 3 into 3q square into 2, just like a plus b the whole cube gives us a cube plus 3a square b plus 3ab square plus b cube. Here we'll write 3q the whole cube gives 27q cube. 3 into 3q square into 2 gives us 54q square. 3 into 3q into 2 square gives us 36q. We'll separate this equation and we'll get 2 as 8. Leave plus 8 untouched. Why? Because we have to prove, as per the given question, that it is of the form 9m where remainder r is equal to 0. It has to be of the form 9m plus 1 where remainder r is equal to 1, and it has to be of the form 9m plus 8 where remainder r is equal to, where we take the divisor b is equal to 3, which is also a factor of 9. So what we'll do, we'll extract 9 from these three equations and we'll get 9 into 3q cube plus 6q square plus 4q under bracket plus 8, which means it is of the form 9m plus 8. Hence proved, any positive integers with r is equal to 0, a cube is of the form 9m, but r is equal to 1, a cube is of the form 9m plus 1, and r is equal to 2, a cube is equal to, or is of the form 9m plus 8. Okay, these were the two important questions which had to be discussed separately. These are the conclusions prepared. So where remainder r is equal to 0, base form 3q, result 3m, squaring or for cubing result 9m. Where remainder r is equal to 1, base form 3q plus 1. What is 3q plus 1? Where a is equal to 3q plus 1. Here a is equal to 3q, sorry, a is equal to 3q, where a is equal to 3q plus 1, or a is equal to 3q plus 2. Then a is equal to 3q plus 1. The result for the squaring result becomes 3m plus 1. The cubing result becomes 9m plus 1. And for remainder r is equal to 2, a is equal to 3q plus 2 is of the base form. The remainder becomes 3m plus 1. How do we get that? It requires 4 to be split in 3 as 3 plus 1, and for cubing result we get of the form 9m plus 8. So important point, the initial remainder r fundamentally determines the structural form of both squares and cube. So this was an important point to be discussed separately. That's why I had to come up with a different video for these two particular problems of real numbers, and I hope this must be clear now for all of you guys. So in the very next class we'll solve the problems related to exercise 1.2 in a very detailed manner. Thank you very much, students. If you like my video, please subscribe, like and share. Thank you very much.